Welcome to the video lecture on modeling with quadratic functions. This is probably one of students' least favorite videos to watch because this is where we're going to learn about how to solve word problems. Now, it's impossible to kind of generalize every single word problem to be the same type of problem, but we are going to learn some strategies in this lecture on how to approach each problem kind of the same way and help think about each problem the same way so they become a little bit more manageable. Now, before we jump into all of our word problems, we're going to start with two special types of problems that are just asking us to practice rewriting a formula in terms of a single variable. So here's our first example. We have that the height of a cone is twice as long as its radius. We want to find a function that models the cone's volume v in terms of its height h. So the first thing that we're going to want to recognize is that in this first sentence it says the height of a cone is twice as long as its radius. So that's a relationship between our height and our radius, and we can kind of write that down as a formula right away. It says that the height is or equals twice the radius. So we can say that our height h equals 2r. Now this is called a constraint. This is something that has to be maintained throughout the entire problem. This is kind of something that we're forced to do. What we want to figure out though is the cone's volume, and that's going to be kind of what we call our objective function. So our objective typically will be something we want to maximize or minimize, but in this problem we're not going to go quite that far. Here we just want to find a formula for this volume of a cone in terms of its height h. So first thing we have to remember is what's the volume formula for a cone. Now I would hope that you know this, but if you don't, you can always Google it or look it up in your book. But the volume formula for a cone is v equals 1/3 pi r squared h. And the problem with this is that this volume formula is in terms of a radius r and a height h. And this question is specifically asking us to find it in terms of the height h. So somehow we need to get rid of this r and rewrite it in terms of h. And that is where this constraint is going to help us. So if it's the r that we're trying to get rid of, then we want to go to our constraint and we want to solve that constraint for r. So if we go over here and try to solve this for r, we'd want to divide both sides by 2, and that tells us that a radius must always be h over 2. So now we can take that h over 2 and we can replace that over here for our r and rewrite this formula as v equals 1/3 pi, and instead of r I can type in or write in h over 2 quantity squared and then times that other h. So now this formula only has h's in it instead of both r's and h's. The last thing I need to do is just clean it up. So if I go ahead and I square my h over 2, remember when you square a fraction, you square the top, so h squared, and you square the bottom, which becomes a 4, times our h. And then just multiplying some things together here, h squared times h will be an h cubed. We have a pi there, and a 1/3 times a 1/4 will be a 1/12. So we get 1/12 pi h cubed. And that is our volume in terms of just the height h. Okay, well, let's try this again. Whoops. With just one more example. Express the area of a circle as a function of its circumference. So this time around, we want to find the area of a circle in terms of its circumference. So we know we're talking about circles. I see the word area, I see the word circumference. So let's write down all the formulas we know related to those things. So area of a circle, this is something I would expect you to know. Area of a circle is just pi r squared. And circumference of a circle, also something I would expect you to know, is circumference equals 2 pi r. So now the tricky part is recognizing which one we're supposed to find in terms of what. So here we want the area, so we want this formula area to be in terms of its circumference. And right now the area formula is in terms of the radius. So I kind of need to get rid of this r and I need to turn that r into a circumference. And that's what this formula is going to enable me to do. So just like in the last problem, if we want to get rid of r, then that's what we want to solve this circumference formula for. So we need to solve this for r, which I can easily do by just dividing both sides by 2 pi. So circumference over 2 pi is what r equals. And now I'm going to take that circumference over 2 pi and I'm going to substitute it in right where that r is. So this new formula becomes a equals pi parentheses c over 2 pi quantity squared, and we just need to clean it up a little bit. So I'm going to go ahead and square my fraction. So if I square the top, I get c squared. If I square the bottom, 2 squared becomes a 4, and pi squared becomes pi squared. And this pi out front can cancel with one of the pi's in the bottom. So simplified, this becomes c squared over 4 pi. And there is our area in terms of just circumference. No more radius involved. So then we're done. Okay? All right, so now we're going to kind of expand on that and solve actual word problems by trying to find where a function has a maximum or a minimum. Sometimes these are called optimization problems. But we're going to do very similar steps to what we just did. We're going to read our question very carefully. We're going to model it in words and sort of draw a picture if that's necessary, label everything that we know and that we don't know. We're going to choose our variables carefully. And we're usually going to be able to find some kind of a constraint equation and some kind of objective function. The constraint is the thing that has to be true and maintained throughout the problem, and it's typically an equation. And then the objective function is usually just a formula that represents the thing that we are trying to find the maximum or the minimum of. So maybe a perimeter or an area or a cost, something like that. So what we're going to have to do is put that cost function or that area or whatever that objective function is in terms of a single variable, just like we did in these other two problems, and then find its max or its min. And sometimes we'll be able to find the max or the min by hand, but a lot of times we'll have to use a calculator. Okay, so here's a very typical example. This is called the farmer problem. So, or in this case, I guess it's a rancher. So here we have a rancher with 750 feet of fencing, and he wants to enclose a rectangular area and divide it into 4 pens with fencing parallel to one side of the rectangle. Find the largest possible total area of the 4 pens. So first thing I'm going to do is draw a picture. So we have this big rectangular area, and we want to divide it into 4 pens with the fencing parallel to one side of the rectangle. And this problem probably should be a little bit more specific and say that we want 4 equal-sized pens. So I'm going to chop this up into 4 equal-sized pens. And what I know is that I have 750 feet of fencing. So that is kind of my constraint. So for my constraint equation, it's going to be the amount of fencing that I would need to use around this shape, and that total amount of fencing has to equal 750. Now I can't really write that out unless I put in some variables. And you have some choices here about how you want to label this. You could call this side x, which would also make this x, and this x, and this x, and this x, and this side could be y. Or you could call this whole length y like I did, or you could let each one of these little ones be y. That would also work. It would give you a different looking equation, but it would still give you the same final overall solution. So there's multiple ways to set up the picture and to label the variables. It's kind of up to you how you choose to do it. So let's say we go with how I've already labeled it here. What would be the total amount of fencing that I would need to fill in these pens? So obviously we need fencing here, 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 and here. So that would be a total of 5 X's worth of fencing. Plus, I need fencing on this side and on this side, and those are both Y's. So that would be a total of 2Y. So that's all my fencing, and we were told that that fencing had to equal 750. So that's called my constraint, and your constraint is usually going to be some kind of an equation equal to a number that they give to you in the problem. Now, the objective function is the thing that you are trying to maximize or minimize. And in this particular problem, we're trying to find the largest possible total area. So that means we're trying to kind of find the maximum area. So my objective function should be an area formula. So if I go back to my picture over here, this is just a basic rectangle. What would be the area of the entire space? Not just one of the pens, but all of the pens. Well, the area, since it's just a rectangle, would be this whole length times this whole width. So that's just y times x, or x times y. So my area function is a very simple x times y. Now the problem with that, kind of like in our 2 previous problems when we were talking about volumes and areas, is that this area right here is in terms of 2 different variables, an x and a y. And I can't really work with that until I swap out one of the variables for something else. I want this to be a formula for area, maybe just in terms of x's, or you could do just in terms of y's. It's really up to you. So let's say I wanted to make this be just in terms of x's. That means I need to get rid of this y and rewrite it in terms of some x's. And that's what this constraint enables us to do. So if we want to get rid of the y over here, then I want to solve this for y down here. So I might subtract 5x from both sides, and then divide by 2. And this tells me that y has to equal 750 minus 5x all over 2. And I'm going to take that whole expression for y, and I'm going to put that right here. So my new area formula becomes x times 750 minus 5x all over 2. Okay, so now let's just clean it up a little bit. So I might rewrite this. You could do 750 over 2 and 5x over 2. So that's like 375 minus 5 halves x. So if I rewrite it in that form, it makes it a little easier to distribute my x out front. And so I can think of my area as being 375 times x minus 5 halves, and x times x becomes x squared. So here's my new area function just in terms of x's. That's the thing that you want to get to. And you're only going to be able to get to that if you use your constraint to eliminate one of the variables. Now, once you get to your formula or your objective in terms of just x's, now you want to look more closely at that formula and decide whether this is a maximum that you can figure out by hand or whether or not you're going to need a calculator. In this case, what you should recognize is that this is just a quadratic function because of that x squared, and it has a negative coefficient. And what we know about negative quadratics is that those are just parabolas that point down. And so therefore it must have a max, and the max has to be at the vertex. And we have learned how to find the vertex of a parabola using a formula. So this is something we can figure out by hand. So to find this vertex, it's just going to be using the vertex formula, which says that the x-coordinate would be minus b over 2a. And in this problem, the b is this 375, and the a is this negative 5 halves. So the 2's would cancel here in the bottom, and we end up getting negative 375 over negative 5, which would give me an x that's equal to 75. So once you've figured out what your x is, make sure you look back at the original problem and figure out what is it that they are actually asking for. And typically in a problem like this, they're either going to ask for the dimensions, which would be both x and y, or they're going to ask for the area. And if we read our question here, it says find the largest possible total area of the 4 pens. So this one's actually asking us just for the area. We don't really need to know what y is. If you did want to know what y is, you could go back to this constraint right here and plug in 75 for the x, and that would tell you what the y would have to be. But since it doesn't ask me that, I'm going to just find my area. Now how do I find my area? Well, I have to go back to my area function. I could do it here, but that would require knowing x and y, or I could go to here and plug in 75 for these two x's. So that's what I'm going to do. So 375 times 75 minus 5 halves, 75 squared. And you just want to punch that into your calculator, and that's going to give you 14,062.5. Now what kind of units should this have? Well, it's an area, and our units earlier in the problem were feet, so units for area would be feet squared. So there is our final solution. That is the largest possible area that we could have for all 4 pens. And that's called the farmer problem, and you're probably going to see something like that on a test for sure. Okay, so the next kind of problem that we're going to look at is the following. It says find the dimensions of the rectangle with the largest area having one side on the positive x-axis, one side on the positive y-axis, and its upper right corner on the line 3x plus 6y equals to 6. So this is a problem where we probably want to draw a picture so we can visualize what we're talking about here. So we're going to have a graph, and we have this line 3x plus 6y equals to 6. So it might be helpful to graph that line so we can kind of visualize what's going on. And when I see a line that's in this kind of standard form, to me, my easiest way of graphing it is just to find the zeros. You can do that a different way. If you prefer to find the slope, that's fine too, but I'm just going to plug in my zeros. So if I let x be 0, this whole term goes away, and 6y equals to 6 when y is 1. If I let y be 0, then this whole term goes away, and 3x will equal to 6 when x is 2. So that means I'm going to have a point at 0, 1, and 2, 0, and I'm going to just have a line through those 2 points. So now what we have here is a rectangle inside of this first quadrant little triangle that we see. So we've kind of got this first positive x-axis, positive y-axis, and this line. So there's kind of that little red triangle there. And if we visualize, there's a little rectangle inside of here. And that rectangle is going to hit right at some point x, y. Now I may not know yet what that x and that y is, but I know that this dimension is the x and this dimension is the y. So you kind of have this little rectangle where here's x and here's y. And the only thing I know about x and y is that they have to be a point on this line. And that is exactly our constraint. The fact that the corner of this little rectangle is hitting somewhere on the line, so this x and this y always has to satisfy the relationship that 3x plus 6y equals to 6, because that's always going to be the point on our line. So this is actually our constraint in this problem. Our constraint is the equation of the line and the fact that we are always on that line. So what's the objective then? What is it we're trying to maximize or minimize here? So if you look at the equation, or look at the sentence, I should say, we are being asked to find the largest area of this rectangle. So if this is my rectangle, what is its biggest area? That's what we're trying to figure out. We're trying to find maximum area. So our objective function is just an area function. And guess what? It's another rectangle. So we know area of a rectangle is just length times width. So in this case, that would just be x times y, just like we had before. So, just like we had before, the problem with this is that it has an x and a y in it, and we need to get rid of one of those variables so that we can write this all in terms of x's or all in terms of y's. It really doesn't matter. So, let's say we want to get rid of y again. Then that's where we go to our constraint, and we solve our constraint for y. So I can do that by subtracting 3x, and then dividing everything by 6. And if I reduce that, I get y equals 1 minus 1/2 x. And I can take that expression and I can substitute it in for this y so that my new area function becomes x times, and then instead of y, I'm going to use 1 minus 1/2 x. And you want to clean that up so that you can see what kind of function it is you're really dealing with. So if I distribute my x, I'll get x times 1 is x minus x times 1/2 x is 1/2 x squared. So good news is we now have this area function entirely in terms of x's. The other good news is if you look at that function, it's quadratic. And it's a quadratic with a negative coefficient, so it's going to be pointing down again, which means if it's going to have a max, it has to be at the vertex. And we have a way of finding a vertex by hand without a calculator. So this is another problem that we should be able to solve for it by hand. So let's find the vertex. The vertex is going to be at minus b over 2a. That's what the x value will be. So in this case, the b here is 1, because that's the coefficient of our x term. And the a is this negative 1/2. And if I simplify here, 2 times negative 1/2 is negative 1, and negative 1 over negative 1 becomes positive 1. So that's what x needs to be in order for this triangle to be its max, or in order for this rectangle to be its max. Okay? So look back at the original problem. What is it that they want to know? Do they want to know the dimensions, or do they want to know the area? And in this problem, it says find the dimensions. So we just found out what x needs to be. X needs to be 1. So how would we find out what the y dimension needs to be? And that's easy to find because that's always going to be determined by your constraint. So we can go back over to here and we can substitute in a value of 1 for this x, and that will tell me what the y value has to be that goes with that. And we just get 1 minus 1/2, which we know is 1/2. So x is 1 and y is 1/2, and so my dimensions of this rectangle would be 1 by 1/2. And there's our final answer. Okay. All right. So the next kind of problem that we're going to look at is another very typical kind of word problem that you'll see in just about every math textbook. And this is called the Norman window problem. So a Norman window is basically just a window that has a special shape. It's a rectangle with a little semicircle on top. So here's what we want. We want a Norman window to be constructed by joining a semicircle to the top of an ordinary rectangular window. Find the dimensions of a Norman window of maximum area if the total perimeter is 16 feet. So there's a number right there, 16 feet, and that's perimeter. So that is kind of our constraint. That's what we have to maintain throughout this problem. So our constraint is the fact that the perimeter needs to equal 16 feet. So in order to come up with an equation for that, we're going to need some variables over here. And we know we are talking about a semicircle, so think about what it would mean to be sort of a perimeter of a semicircle. Well, we have a fancy name for that. The perimeter of any kind of a circle is also called circumference. And one of the formulas that we just talked about earlier was that circumference of a whole circle is 2 pi r. So it would be helpful to have a radius labeled on this picture and use a radius as kind of one of our dimensions. So in this case, the radius would be that little r right there. And the circumference of this semicircle then would be half of the circumference of a whole circle. And half of 2 pi r is just going to be pi r. So the perimeter of just the top half of the circle would be pi r. But what's the perimeter of the rest of the window? We know we need this much covered, and we just figured that out. But we also have perimeter here, here, and here. So these two guys on the sides, those need a name. So maybe I'll call each of those y. So I know that I'm going to need some perimeter for both of those, and that would contribute 2y to my total perimeter. And then look down here. Instead of calling this x, notice that that is really just 2r, because if half of it is r, then the whole length across would be 2r. And so by using a 2r, we're reducing the number of variables that we need to have in this problem, which is going to make our life easier. So we have the perimeter of the top half of the circle, the perimeter of these two sides, and the perimeter of the bottom part. And so that's all of this, and that has to equal 16. So that's our constraint. Now we move to the objective. So what is it we're trying to maximize or minimize here? In this case, we want to find the maximum area. So our objective function needs to be some kind of area function. So if you look at our shape over here, we've got two different pieces. We've got the rectangular piece, and then we have the semicircle on top. So what would be the area of the semicircle piece? Well, area of a whole circle is pi r squared. So area of half of a circle would be a half pi r squared. So that's going to be the area of just the semicircular part. Then we have to add to that the area of this rectangular part. And area of a rectangle is just length times width. So that's just going to be 2r times y. So plus 2ry. Now this doesn't equal a number. Remember, this is our objective. Our objective is usually just a formula. The problem with it is that it has r's and y's, and we need to get rid of one of these variables so that we can have a new formula just in terms of r or just in terms of y. Now, how do you decide which one to get rid of? Well, look for whatever's easiest. If I wanted to get rid of the r's, then I'd have to do a substitution here and a substitution here, which is a little bit of work. And I'd have to be able to solve this for r, and I've got two r terms, which makes that a little harder to do. Instead, if I just replace y and come over here, it's not so bad to solve this constraint for y, because there's only the one y term. So if I subtract the two r terms to the other side, that gets me the y term by itself, and then I can divide everything by 2, and that isn't too much work to figure out what y is. So it looks like y is going to be 8 minus, I'm going to write this as 1/2 pi r, and then minus r. And now I'm going to take all of that, and I'm going to put that right here where this y is. So my new area function would be 1/2 pi r squared plus 2r times 8 minus 1/2 pi r minus r. And we definitely need to clean this up a little bit here. So I'm going to get 1/2 pi r squared plus, and if I distribute, I'm going to get 16r minus the 2 and the 1/2 cancel, and r times pi r is pi r squared. And then 2r times a minus r is minus 2r squared. Now, if you look at this, it's a bit of a mess, but there are actually two like terms here that I could combine. A 1/2 pi r squared and a minus pi r squared, those are like terms because they both have a pi and they both have an r squared. And this one's a 1/2, a positive 1/2, and this one has a coefficient of -1. So what's a half minus a 1? Well, that's a negative a half. So this is going to be negative a half pi r squared plus 16r minus 2r squared. You can't really combine it much more than that. These r squared terms are alike, but this one doesn't have a pi, so it doesn't make it easy to kind of combine these. If you want to put it in a slightly different order, you certainly could. You could put the 16r term first and then the other terms after it. It doesn't really matter what order it comes in. But here's our area function. Now technically, because we have r squareds, this is quadratic, and the r squared terms both have negative coefficients. So this technically is a parabola that points down. So technically we could use the vertex formula to find the maximum, the vertex, by hand. However, it's really messy because of the pi's. So in a problem like this, where you've got yucky decimals involved and bad numbers, it's perfectly okay to find the maximum not by hand, but instead by using a calculator. So how would you do that? Well, you would take this whole big area function right here, and you would need to type it into your y equals and graph it. So let me pull up my calculator. Hopefully this works. And I have a bunch of stuff in here, but if you look at y1, I have typed in 16x minus 2x squared minus pi over 2x squared. So that's exactly this formula, but I used x's instead of r's, and that's because the calculator only lets me use x's here. So next thing I want to do is I want to graph this, but I want to make sure that I'm graphing it in a good window. So if I start with just a standard window and do a zoom standard, zoom 6, it's got that parabola shape, but remember what we're looking for? We're looking for the maximum, and I can't see that max because it's kind of hiding up here. And that means I really need to boost up my y max so that I can see that maximum. So I'm going to adjust my window dimensions, and maybe I will just change my y max to maybe a 20. And let's see if that helps us see that maximum a little bit better. There you go. So once you have a good graph and you can clearly see where that maximum is, now you need to find it. And that we can do using this calc command. So if I do second trace, and then do maximum, number 4, and then we're just going to get close to our max on the left side and on the right side, and then give it a guess, and there's the coordinates of my maximum. Now notice there's an x and there's a y, so it's important to know what's what. The x here, remember, was the r that I had over here. Okay, so our x of 2.24, that's what our radius r needs to be a maximum. This y value is not the same as this y that we had over here in our picture. Because what did y equal in my y equals over here? Remember, this y on this side represented area. It was this formula right here. This was an area formula. So on your notes, in your homework, or in a test, what I would expect to see if you're using your calculator to get this answer is I must see a graph drawn in your work of the shape of the graph that you did in your calculator. So we got a parabola. I would really like to see the window dimensions that you used, which for us were -10 to 10 for the x's and -10 to 20 for the y's. And I have to see that vertex labeled. And this was at about 2.24 for the x and it was about 17.92 for the y value. And then you need to recognize what these numbers mean. So remember, the x was the variable we had over here on the right side. So that's your r. The y is what this represented on the left side, and for us that was area. So once we have the coordinates of our vertex, of our maximum, then we just have to look back at the original problem and figure out what is it they wanted to know. Did they want to know area, or did they want to know the radius and the other dimensions? Well, in this case, it wants the dimensions. So we know what the radius should be. The radius needs to be 2.24, and our units here were feet. But in our picture over here, that was r. We had another dimension, which was y. So to find out what y is, we have to go back to that constraint. That's going to be your quickest way to find out what that second dimension is. And all I have to do is take 2.24 and plug that in for each of these r's. And you know what? I don't have it handy at the moment, but if you have a lot of these decimals written down, it'll make your answer be a lot more accurate. So if it's at all possible, write down a few more digits than I have here, so that when you plug them into this formula for y, you're going to get a much more exact value for y. And it turns out you actually get back the same thing. You get 2.24 back again. And this would be feet. So our dimensions would be 2.24 feet for the radius, and the y would also be 2.24 feet. Okay? All right. Okay, the next example is another very famous kind of math problem that you'll see not just in this class, but in many other future math classes that you take. And this is called the box problem. So here's what we're doing. We're going to create our own box. And we're going to do that by taking a rectangular piece of cardboard that in this case is 12 inches by 20 inches. So let me draw that. So we have 12 inches here and 20 inches here. And what we're going to do is we're going to cut out equal squares of side x at each corner. So I'm going to cut out a little square here, 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 and here. And each of these little squares is x by x. So to visualize what's going to happen, imagine cutting out those corners. So now your little piece of paper is going to look like this. Okay? And then imagine folding along these little dashed lines. And that's going to create 4 little flaps that I'm going to fold up. And if I fold them up, I'm going to end up with a box that doesn't have a top that looks like this. Okay? So what we want to do is figure out what should this x be so that we can have the box that has the largest volume possible. So if we want to find the volume of this box, think about what the volume formula of a box is. Hopefully you know that. It's just length times width times height. So I need to know what the length, the width, and the height of this box are going to be. So let's think about it for a minute. Where does this height come from? Well, the height comes from folding up these little flaps. And these little flaps have a height right here that's equal to x. So this little height right here is just that little x that we cut away. Now for the length over here, the length comes from this length right here. Okay? And that comes from this distance from here to here. So how could we figure out what that is in terms of x? Well, we know this whole length from here to here is 12, and we're cutting away an x and an x. So this new length in the middle must be 12 minus the 2 x's that we cut from the 2 corners. Okay? And likewise, if we want this width here, that comes from this length right there, which is this distance right here. And that's this whole 20 minus this little x that we cut away and minus this little x that we cut away. So this must be 20 minus 2x. Okay, so now we have our 3 dimensions. We have our length, our width, and our height. So our volume is just going to be the 3 of those multiplied together. And you could multiply them in any order you like. I'm going to put the x first, and then I'll do 12 minus 2x, and then 20 minus 2x. Okay? Now that is our objective function. That's what we want to find the largest volume. So we want to maximize this volume. So we have an objective. You might ask, well, where's the constraint in this problem? And in fact, we really didn't have a separate constraint equation, but there was a constraint. The constraint was the fact that our dimensions of our original piece of paper were 12 by 20. And so instead of creating a new variable like a y, we just built into our length and our width of our box over here the fact that when we cut away those corners, we had to subtract it from the original dimensions. And so we kind of built in our constraint into this objective function. So you don't really have a separate constraint for this particular type of problem. All right, so now that we have this volume formula, the good news is it's entirely in terms of x's, so you don't have to do any changing of variables. The bad news is, if you were to FOIL all this out, which you're welcome to do but is not necessary, what degree would it be? Well, it would be an x times an x times an x, so that would be an x cubed. We do not have a vertex formula for cubic functions. We only have a vertex formula for quadratic functions. So this is not something that we could find the maximum of by hand. The only way to find this max would be to graph it. So this is one that we are going to have to use our calculator for. So we're going to go to our y equals, and we're going to type in this function into our y equals. So if we arrow down here, I'm going to turn off this first graph, and I'm going to go down and turn on the second one. So here's my function, x times 12 minus 2x times 20 minus 2x. So we want to graph this, and we want to be able to see where the maximum volume occurs. And in order to do that, we're going to have to make sure that we get a good window so that we can see what's happening. So I'm going to start with just a zoom standard, because I don't really know what to expect yet. And we know this is supposed to be cubic, but the graph that I'm seeing right here really doesn't look very cubic. So we definitely want to adjust our window dimensions. And if we think about this for a minute, these x's were lengths, so those can really only be positive, and the y's are our volumes, and those can only be positive. So for my window dimensions, maybe I'll let my x min be 0, and maybe I'll boost up my x max a little bit. Let's try 15. And then for my y's, I'll start my y min at 0, because we're talking about volumes here. And my y max, I'm going to let that be quite a bit bigger, because if I've got a 12 times a 20, if you were to multiply 12 times 20, that's going to be something in the hundreds. So I'm probably going to need some numbers that are in the hundreds as well. So maybe I'll guess, let's just try 300 to start. I might need to adjust my y scale. Maybe I'll go by 20s, just so that I have a little bit better scale. And let's graph. So here's our cubic. So I can see a nice maximum right here. So that's going to be the place where my volume will be max. So that's what we want to locate next. So to find that, we're going to go to calculate, and we're going to hit number 4, and we're just going to go on over until we get a little to the left, hit enter, a little to the right, hit enter, and then give it a guess. And 2.427 would be the x value that we had in our formula over here. So that's the x's that we would be cutting out of the corners. And this y value, this 262.68, remember, that's what the left side of this formula was, and that was volume. So in our work, we would want to show that graph, which looked kind of like this, and I would want to label my maximum, which had coordinates 2.427, comma 262.69. And my window dimensions here were 0, 15 for the x's and 0, 300 for the y's. So let's figure out what these mean again. Remember, this x is the same x that we had in our formula, which was the same as this x that we're cutting from the corners. So the x we would need for our largest box would be 2.4 inches cut from each corner. This number for the y coordinate represents what's on this side. So for us, that would be a volume. And so if we look back at question A, what did they want? It says find the largest volume that such a box can have. Well, that would be this volume that we found at the max. So our largest volume would have to be 262.69. And what kind of units should a volume have? Well, since these were in inches, we would want inches cubed. So that is our volume answer for part A. Now for part B. For part B, it says find the values of x for which the volume is greater than 200 cubic inches. So how would we figure that out? Well, here's our graph. This is the graph of all the possible volumes that could exist for all the choices of x that we could cut away. So if we want to know when is this volume bigger than 200, it makes sense to kind of put in 200 as kind of like a horizontal line and see where does this graph lie above it. And I see that happens here, and in this case it also happens over here. So to figure that out, I'm going to go back to my graph, and I'm going to go to my y equals, and oops, I don't have it typed in here. Let's add one in here. I'm going to go down here, and let's add in 200 into our y equals, and I'm going to graph it right on top of my volume graph. And so that's where it intersects the volumes. So any place where the graph lies above this horizontal line would be any place where the volume is bigger than 200. So to give an answer, we're going to need to know where all of these x's are and where all of these x's are. And that requires knowing these intersection points. And we can find those by using our calc command. So if I do second trace to get to calc, and I do option 5 for intersect, then I can find each of these intersection points. So the first one would be at about 1.17, and I'll write these down in a minute. And then the second one would be at 3.897, and then the last one way over here keep going until you see it. It's going to be at about 10.928. So on your graph over here, we are going to label each of those intersection points. So this one was 1.1737, comma 200. This one was at 3.897, comma 200, and this one was at 10.928, comma 200. So in terms of where is this graph above 200, all of these x's, which would be from 1.737 up to 3.897. And we want to be strictly greater than 200, so I don't want to actually use those endpoints. I want to use parentheses instead of a bracket. So we could say 1.737 up to 3.897. All of those x's would give me a volume greater than 200. And then it also looks like I'm greater than 200 over here. And so that would be from 10.928 on to infinity, because the graph doesn't come back down again. But there's something wrong with that. So think about the context of the question. Remember that these are word problems, and so there's always going to be some kind of background, some kind of context that you have to always keep in the back of your mind. Does it make sense for x to be 1.7, for x to be 3.8, and for x to be 10.928? So remember, x was how much we were cutting away from each of these corners. And if you think about it, if x was 10.928, and I cut away 10.928 from the right side and from the left side, there wouldn't be enough paper to be able to do that, because my shortest length here is 12. So if I cut away over 21 inches worth of paper by cutting out 10.9 from each side, I'm going to not have any side left. So these don't work. None of these points will work because they're too big. The paper isn't large enough. So they're not even in the domain or in the context of this question. So in this case, my only solution is going to be the case where we have just, whoops, I didn't mean to erase it, where we just have the 1.1737 up to 3.897. So this won't work because it's too big, and only these values of x will actually be my solution. Okay, and that would be the answer for part B. All of those x's give you a volume greater than 200. Okay, so the next example here, again another pretty common problem that you'll see in a lot of these math textbooks, is the wire problem. So in this case, we have a wire that is 10 meters long, and it's being cut into two pieces. So we are going to chop it somewhere. I'll just say I chop it right here. And one piece is going to be shaped as a square, and the other piece will be shaped as a circle. So in part A, we want to find a function that models the total area in terms of the length x of the piece of wire bent into a circle. So what does all of that mean? Well, it means if I cut this 10-meter long wire into two pieces, maybe I'll call this much of it x. If that much of it is x, what does that force this second piece over here to be? Well, since the whole thing is 10, and this much of it is x, then this second piece must be 10 minus x, so that they add together to 10, right? And so what we're doing in part A is we're taking the piece that's called x, and we're wrapping it around to form a circle. And we're going to take the piece that's labeled 10 minus x, and we're going to wrap that around and form a square. And what we want to do for part A is find a function that models the total area of both of these. So I want to add the area of the circle plus the area of the square. Okay, so area of a circle is pi r squared. Area of a square, if we say this square has side s everywhere, then its area would be side squared. So that would be my total area function. Now the problem is, this area function right here uses r's and s's, but the question asks us to use x's. So somehow we've got to get rid of r, and we have to get rid of s, both, and turn them into x's. So we're going to need a constraint or two to be able to figure that out. So if we go over here to our picture, we must be missing some information. We need some constraints involved. So think about what's happening. We're taking this length of wire x long and we're wrapping it around to form this circle. So that x really represents the circumference of this circle. So if circumference formula is 2 pi r, then in this scenario, x must equal 2 pi r. And remember, we said over here we wanted to get rid of r and turn it into an x. So this constraint right here is what we're going to use to do that, because we're going to solve this for r, because r is the thing we're trying to get rid of. And this gives us a formula that we can now use over here to replace that r and turn it into an x. So this is going to become pi times x over 2 pi quantity squared. Now we're going to do the same kind of thing for this s squared. So let's go over to our square over here. Notice that the 10 minus x is getting wrapped around the outside of my square. So the 10 minus x is the perimeter of this square. And perimeter of a square is just side plus side plus side plus side, or 4 sides. And we want that perimeter to be 10 minus x. So if it's s that we're trying to get rid of, then over here we want to solve this for s by dividing by 4. And so I can take this and I can substitute that right here for s and rewrite this as 10 minus x all over 4 quantity squared. And now I have a new area function that only has x's in it. There's not a whole lot of simplifying that I can do here, but I will clean this up a little bit. I'm going to go ahead and square this fraction. So if I square the top, that gives me x squared. If I square the bottom, 2 squared becomes 4, pi squared becomes pi squared. And I can cancel out one of those pi's. So this will become x squared over 4 pi. And then for this one, I'm not going to bother to FOIL the top. I'm just going to leave it as parentheses 10 minus x quantity squared. But I will go ahead and square the bottom and turn that into a 16. So here is my new area function, only in terms of x's. Now notice that, again, it is quadratic because it does have x squareds in it, but it's much too messy for us to try to work with by hand. You wouldn't want to use minus b over 2a here because you just got too much stuff going on that's too complicated. So the best way to find this maximum or minimum area would be to graph it. So part A, we're actually done. Part A was just to find a function that models the area. And so that is just this function that we just came up with. So that's your answer for A. For part B, it wants the minimum total area. So we're going to want to graph this, and we're going to use our calculator because it's too messy to try to do by hand, and we're going to locate the minimum on that graph. So let's pull up our calculator. I need to turn off the graphs we were just using because we don't need them anymore. And I'm going to turn on this one right here. Now notice how I'm typing this in. This is really important. When you're typing in this function, it's pretty messy. Notice that this denominator has both a 4 and a pi in it. So when you type it in, you have to use parentheses around the 4 and the pi. Otherwise, you're not going to be looking at the right graph. So that's what I did up here. I've got x squared divided by parentheses 4 pi plus 10 minus x squared all over 16. So I want to turn that graph on. And let's start with the zoom standard to get a feel for what the graph looks like. And remember, we're trying to find the minimum. So as soon as you get a window where you can see that minimum, you're good. You don't have to do anything else. And I can see that there's a minimum right about here. So to find it, I'm going to do second trace to calculate. I'm going to do number 3 this time to find a min. And I'm going to go a little to the left, a little to the right, and then give it a guess. And then I'm going to copy this picture onto my work and label them in and write down my window dimensions. So here was that graph. It looked kind of like this. And we had a min at 4.399, comma 3.500. The window dimensions were just negative 10 to 10 by negative 10 to 10. And this x value is the same x that I had over here, which is the same x that was my cut piece of wire. So this is your x. The y coordinate is what this function represented, which in this case was an area. So the y value here is our area. And what does the question want to know? It says find the value of x. So it just wants to know what x was, and that's this 4.399. And units on this, since we were using a wire that was 10 meters long, this must mean that we need to cut our x at 4.399 meters to form the circle, and then the remaining length would form the square, and that's going to give us our minimum total area. All right, next example. This one's also kind of a common one as well. So we're going to need a picture here, which I'm going to draw for you to help explain what the scenario is that's going on. So here what we have is an island 2 miles from the nearest point P on a straight shoreline. So imagine that we have this island here that is exactly 2 miles from point P on this shoreline. A town is 12 miles down the shore from point P. So over here is town, and that's 12 miles away. Assume that a person can row a boat at a rate of 3 miles per hour, and the same person can walk 5 miles per hour. Find a function that models the time t needed for the trip to get from the island to town. And where should the person land so that he reaches the town as soon as possible? Okay? So here's what you have to visualize. This person is stranded on the island, and they need to get to town. So either they could go straight across the 2 miles and then go 12 miles down shore, or they could row a little ways and then walk the rest of the way. So we want to know, where does he need to land? Where should this point be right here so that he gets to town as quickly as possible? And if you want to get there as quickly as possible, that means you want to minimize your time. So we're trying to find a time function in part A, and then we're trying to find the minimum of that time in part B. Okay? So, how do we find time? Well, we've got some distances going on in this picture, and we have some rates given to us in the problem. So, think about the relationship between distances and rates. We know that distance equals rate times time. So how would you find the time if you knew the distance and the rate? Well, we could divide by the rate, and that tells me that time is distance over rate. So what we're going to do to find this time function is we're going to calculate the time it takes to row, which is this part of the journey right here, plus the time it takes to walk, which is this part of the journey. Okay? So we need a variable in here, and you can choose. I'm going to choose to let x be this distance here, and that would force this to be 12 minus x. You could also have chosen this to be x, and then this much would be 12 minus x. It doesn't matter which way you choose to do it. So, if we want to figure out the time to row, then we need to know the distance to row divided by the rate to row. because we said time was distance over rate. And to get the time to walk, we need the distance to walk divided by the rate to walk. So some good news is we already know these two rates. They told us that in the problem. So the rate to row was 3, and the rate to walk was 5. But the distance to row is this hypotenuse, and you can assume that this is a right angle right here. So we're needing to know the hypotenuse of this right triangle. And hopefully you remember from geometry that every right triangle has to satisfy the Pythagorean theorem. So if I were to call this hypotenuse C, then according to the Pythagorean theorem, the leg squared, 2 squared, plus the other leg squared, x squared, has to equal the hypotenuse squared. And that means 4 plus x squared has to equal c squared. And to solve for just to c, we could take a square root of both sides. And so this hypotenuse right here must be square root of 4 plus x squared. And that is our distance to row, because it's that long that we have to row through the water. So that's our numerator. What is our distance to walk? Well, once we land on shore here, then this is how far we have to walk, and we called that 12 minus x. So the distance to walk would just be 12 minus x. So here is our new time function. This is the time function, only in terms of x's, that models the time it takes to get from the island to town. And that's exactly what they were asking for in part A. Now for part B, we want to find where we land so that we reach the town as soon as possible. So in other words, we want to minimize this time. So we want to find the minimum of this function. Now because of that radical in there, this is not a nice quadratic function. This isn't something we could ever work with by hand. So the only way to find the minimum is going to be to use a calculator. So we're going to have to graph this, get a good window, and then locate the minimum using that calc command to find the min. So let's go to our calculator, go to y equals. I'm going to turn off the last one we did, and I'm going to turn on this new one. So here's the square root of x squared plus 4 all over 3 plus 12 minus x all over 5. So that was that time function that we just figured out. And now we want to graph it, so I'll start with a zoom standard. And we just want a window where we can see a minimum in. And as long as we can see a min, we don't have to do any extra work. So I can kind of see that there's a minimum somewhere around here. And you can shorten up your window dimensions if you want to make it a little bit more obvious, or you can just go with what you've got right here. And I'm going to do that and do my second trace to get to min. And then I'm just going to go a little to the left, a little to the right. You can watch those y values. When they start getting bigger again, then you know you've gone past the min. And then a little to the middle. And there's my minimum. So the x value is about 1.5 and the y value is about 2.93. So we want to graph that in our work. And this was just a negative 10 to 10 for the x's and a negative 10 to 10 for the y's. And I'm going to label this minimum, and the x was at about 1.5 and the y value was about 2.93. So what do these numbers mean? Well, the x was the x that we had in this formula. So that's just our x, which in our picture up here was where we needed to land away from P. The y value up here is what this function represented, which in this case was time. So this would be our time. And our units for that time would be in hours because our rates were miles per hour. So it's going to take us almost 3 hours to complete the journey. Now what did the question want to know? for part B, it says where should the person land. So the person needs to land at 1.5 miles away from P to minimize your time. You could also say if I'm landing 1.5 miles away from P, that means that I'm 10.5 miles away from town. So it kind of depends on how you want to word it. So you could also say that you need to land 10.5 miles from town. Either answer would be correct. Okay, we're down to our last example, but it has several parts. So this is another farmer problem, but with a couple of variations to it. So what we have is a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 200,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? So let's draw a picture. We have kind of this river over here, and then we have a rectangular pasture that's right up against it. So let's give some dimensions to this rectangle. I will call this side X, and then these two sides would be Y. So what is our constraint for this problem? Well, we know that the pasture must contain 200,000 square meters. So think about the units of that. Square meters is a unit of measurement for area. So this 200,000 is actually an area. In the previous problems, our constraint was a perimeter, but this time around it's an area. So what's the area of this rectangular shape? Well, it's just length times width, so X times Y must equal 200,000. So there's our constraint. What's our objective? What are we trying to maximize or minimize? So in this case, it says what dimensions would require the least amount of fencing. So we want the minimum amount of fencing. So our objective function is going to be the amount of fencing needed, which is kind of like perimeter. And remember that it said we do not need fencing along the river. So we only need to put fencing here and here, which would be 2 Y's, and here, which would be 1 X. So our total fencing needed would be X plus 2Y. Now right now, that objective function has X's and Y's in it. So we need to get rid of one of those variables, either one, and resubstitute back in terms of the other variables so that we can figure out how to find this min. So my tradition is usually to get rid of Y. Really doesn't matter. So I am going to go back to my constraint, and if I want to get rid of Y, I'm going to solve this constraint for Y. And I can do that by just dividing by X. And then I can use that over here to substitute in and get my new fencing equation, which is X plus 2 times 200,000 over X, or if I simplify it, X plus 400,000 over X. Alright, so there's our fencing function just in terms of X. We did that because now we need to find its min. We want the least amount. So where does this have a min? So you want to be asking yourself, is this something I could do by hand? And the question or the answer is no, because this is not a quadratic function. When you're dividing by X like this, that's not a parabola. So the only way to find the minimum of this function is to do it with a graph. So we're going to pull up our calculator, and we're going to go to y equals, oops, sorry about that, and I'm going to go and I'm going to turn off this graph, and I'm going to turn on this one, and here's that x plus 400,000 divided by x. Now 400,000, that's a really big number. So chances are we're going to need some pretty big window dimensions. So let's just go ahead and go to our window. And we're talking about fencing, and we're talking about areas, and those are all things that need to be positive. So I'm going to let my x-min start at 0, and I'm going to choose a fairly large x, maybe 5,000. And I might need to adjust my x scale so it's pretty big too. And I'll let my y-min be 0, and let's let our y-max be pretty big. Maybe I'll start with 10,000. And I'll let my y-scale be 1,000 as well. So cross our fingers and hope we see a good graph. We're looking for a min. And as long as you can get a window that shows that min, you're good. And I see there's a min right about here. So I'm going to find it by doing second trace, number 3 for min. And I'm going to go a little to the left. And a little to the right. And then give it a guess. So 632 and 1,264. So I'm going to draw that on my paper. There we go. And I had a graph that looked kind of like this. Oops. And if I label that min, it was at 632 approximately, and 1,264 approximately. The x value here is the x that we had in our formula. The y value here is what this function represented, which was fencing. So what do we need to give for this answer? We need the dimensions. So to find the dimensions here, we need our x value, which we already figured out. So our x dimension is going to be, let's see if we can fix this, 632. I don't know why it's doing that, sorry about it. And that would be meters. And then how would we find the y value? Well, go back to your constraint, and you can plug in 632 right there. Use your calculator to do that division. And if you punch it in, I'll kind of skip the work there, you'll get about 316 meters. So our dimensions are going to be 632 approximately for the x, and 316 meters approximately for the y. So that's our part A. Alright, so next, now we're going to assume that the farmer has decided to put a special wire fence along the riverside and less expensive fencing along the other 3 sides. The cheaper fencing costs $2 per meter, and the more expensive fencing will cost $5 per meter. Determine a cost function and find the dimensions that will minimize the cost of the fencing. Alright, so if we visualize this time around, we still have our river and our sides, but this time we're putting fencing around, and we get to put $2 on 3 of the sides, but $5 per meter on the river side. So this is going to be the $5 side, and then these are all $2 each. And I'll use the same labeling that I had before. So this was x, so this would be x, and this would be y, and this would be y. So we still have that same constraint in place as before. We still have the constraint that the area, which is in this formula or in this picture, x times y, that's still equal to our 200,000. We haven't lost that. So we know that y is still going to be 200,000 divided by x. But this time around, we're trying to minimize cost. So our objective function is now going to be a cost function that we want to find the minimum of. It's not exactly the same as just fencing. It's cost of fencing. So how would you calculate the cost of your fence? Well, it would be the length of your side times the cost per the length. So in this case, this side would be x times 2, or 2x. This side would be y times 2, or 2y. This side would also be y times 2, or 2y. And then the more expensive side would be x times 5, or 5x. And if you combine your like terms there, that's going to give you 7x plus 4y. So there's our cost function, but it's in terms of x's and y's, and we need to get rid of one of those variables. So I'm going to get rid of y by substituting in that constraint right here. So our new cost function becomes 7x plus 4 times 200,000 all over x, or cost equals 7x plus 800,000 all over x. And we want to minimize that. We want the minimum cost. So again, this is not something that we can work with and do by hand because it's not a quadratic function. So in order to find the min of this, we're going to have to graph it on our calculator, get a good window, and then locate that min. So if I go to my y equals, and I turn off the last one, and I turn on this new one, here's that 7x plus 800,000 all over x. And for my window, let's just stick with the same window we had before and see if that works. Yeah, it's a little narrow. If you wanted to change your y max, maybe your y max doesn't need to be quite as big as 5,000. Maybe I'll just go to 1,000. So there's our nice graph. And if we locate the min, our min is at 338 for the x and 4,732 for the y. So let's draw that. And this was at 338, comma, 4,732. Our window dimensions were 0 to 1,000 for the x's and 0 to 10,000 for the y's. This x value is this x over here, so that's this x dimension. And this y value is our cost. Okay, so what is the question asking for? It wanted a cost function, and we got that right here. And then it wanted the dimensions as well. So the x dimension would need to be about 338 meters. And then to find y, go back to your constraint, and you could type into your calculator 200,000 divided by this 338, and that's going to give you a y that equals about 591. So that would be your meters. And so those are your two dimensions that are going to give you the cheapest cost for the fencing. Okay, so last question is going to be to determine if the farmer has at most $600,000 to spend on fencing, find the range of lengths he can fence along the river to stay within his budget. So we are going to use the same cost function that we had before, and this time around we want to stay under $600 or $6,000. We have that much money to spend. So what's the biggest size amount of fencing that we can use, the biggest field we could fence in and still stay within budget? So to figure that out, it's kind of like our volume of our box problem that we did earlier in this lecture. We already have this nice graph of our cost function already typed into our calculator, and this represents the costs of all of our different types of fencing choices depending on what x and y are. So somewhere we can draw in a horizontal line equal to $6,000 to see where these costs are going to be below $6,000, which would be at all of these points down below. That's what we're trying to figure out. So what does this determine and what does this determine for the x and the y? That's what we're going to try to figure out. So we can do all of this graphically by going to our calculator, and I already have my cost function turned on, and I'm going to add to that horizontal line at 6,000. So I'm going to draw both of these at the same time, and I'm going to see where they intersect. And I shouldn't have to adjust my window dimensions. So if I can find these two intersection points, that will tell me the x's that I'm going to need to use to stay within my budget. So we can use that intersect command, and we can find both of these intersection points. Too far. So 165 would be the x on the left, and if I do the one on the right, then I get 691.98. So let's label those. So this one is about 691.98, and then this one was about 165.16. Okay, and those were the x values. So to answer this question, x would need to be between 165.16 meters and 691.98 meters, or if you wrote it as an interval, 165.16 up to 691.98. If I use those x's, then I'm going to be using costs that are all below $6,000. Now that's what the x dimension needs to be. How would you figure out what the y dimension needs to be that goes with that? Well, remember our constraint. Our constraint was that y was 200,000 over x. So if you plug in each of these x values here, so plug in 165.16 and plug in 691.98, then that's going to give you a y value equal to about 1,211 approximately, and this one is about 289. So the y's would need to be about 1,000. Whoops, I better put this in the different order, right? We want to put the smaller number first on the left and the larger number on the right. So I don't want to start with the bigger number. So I'm going to start with the 289 up to 1,211. So between 289 meters to 1,211 meters. Okay? All right. After all that work, we finally finished. So this ends our video lecture on modeling with quadratic functions. Keep practicing and keep these notes handy when you're working on the homework problems, because your homework problems are probably going to be very similar to these but with different numbers. All right, good luck and have a great day.